So starting with the fact that P plus R times P equals quantity 1 plus R times P, which is easily found, you could use a distributive law here, and you get P and you get RP. Or you could factor this, factor P out of this, and you get this. Okay, using this idea. Okay, if we invest $1,000 at 12%, how much do you have at the end of the year? Well, your interest is 12% of 1,000, that's 120. You add that to your 1,000, you get 1120. More significantly, you get this, which summarizes this calculation. But if you factor the $1,000 out, you get 1 plus 0.12 times $1,000, which is 1.12 times $1,000, just using this idea. And then we ask, what calculation gives the principal after 2 years? That would be 1.12 times the amount you had at the end of 1 year. Even better than that is 1.2 times the quantity 1.12 times $1,000. Might not be totally clear why. That's better. I mean, you can understand why it is. Why is that better? Well, you can go to still better. $1.12 squared times $1,000. Okay, now what about after 3 years? Now I'm just going to write it as 1.12 multiplied by 1.12 squared times $1,000. Which is 1.12 cubed times $1,000. And of course, if you want the amount after 4 years, you multiply this by 1.12, and what do you get? Okay, well, tell me through private chat or public, if you want to show off. What do you have after 4 years? Okay, well, I haven't really given you time, but oh, now you've had time. Figured if I started writing, you'd get it. Okay, that's good. What about after T years? What would you get after T years? Well, I think you're going to get it. I'm not giving you time here, because among other things, I've got the camera on. Be 1.12 T times $1,000. So P of T is $1,000 times 1.12 to the T, where P of T is the principal function. Principal is a function of time. That's not multiplying P by T, that's P of T. Okay, this is an exponential function. Okay, well, actually 1.12t is an exponential function. And 1,000 times 1.12 is vertically stretched exponential function. Well, it gets even better than that. If you sketch the graph of y equals 2 to the x, and I'll just sketch a small graph up here, we'll get a bigger one in a minute, but okay, here's y equals 2 to the x. Okay? It has exactly the same shape as $1,000 times 1.12 to the t. Or $1,000 times 1.12 to the t. But with different scales on your axes. Okay, so one example of an exponential function based on compound interest, which is something that I'm surprised our schools don't teach better. Might not teach all this getting to the exponential function, but the whole idea of compound interest is so important to personal finance, and there's an emphasis on that. Don't know why it's not being taught. I think back in the early 60s, maybe in the late 50s, I learned the thing in middle school. And so did everybody else. Not everybody understood it, but most did. So it's not that hard to understand. Okay, well, point is, it's very important, and it's even more important if you understand that population models work the same as compound interest. And many other models. Okay, population models may be the easiest to understand. The idea here is that the more money you have, the more interest you get. You're taking 12% of bigger and bigger quantities. So this thing grows exponentially. With populations, if you have unrestricted population growth, then the number of new critters that you get is proportional to how many critters you got there to reproduce. Okay, we got deer herds in town, and I'm pretty sure they're growing exponentially. You almost trip over them if you go out for a walk, and you can't grow anything. It's kind of neat having them around, but they're overpopulated. It's not good for them. Okay, so you got population models, and you got compound interest models that behave very similarly. I want to go on to a little more detail about compound interest. But keep in mind that if you have a herd of deer with 1,000 deer growing at 12% a year, you're going to get the identical numbers.